All right, example 4 presents us with a definite integral. Okay, so we're going back to definite integrals here. The first part of this lesson was essentially a redux of our first lesson in this whole entire unit, which was about finding antiderivatives. We just did it using this new symbol. So you might ask yourself, well, why didn't we just start with using that symbol? Well, some books do. The Larson textbook does. Ours does not. I tend to like that better because it kind of preserves a little bit of mystery here, and that whole reveal that happens with the fundamental theorem of calculus. I think it's a little bit more powerful when we don't know that that's what this little symbol represents. Anyway, back to example form 4. Find the definite integral from 0 to 2, 2x cubed minus 6x plus 3 over x squared plus 1. I thought we can't do quotients with respect to x, and interpret your answer in terms of area. Okay, so got to find an antiderivative first of all, and that antiderivative is going to be an x cubed. No, it's not. It's going to be x to the fourth. So 2x to the fourth over 4, which would reduce to a half, minus 6x squared over 2. That's a 2, believe it or not, which would reduce to, come on, scribble, scribble, to a 3. And then finally, like I said, there isn't a quotient unless you already know that this is the antiderivative of arctangent. And this 3 is just going to come along for the ride. So it's going to be 3 arctan of x plus c? No, from 0 to 2. Okay, fundamental theorem of calculus. In this particular case, we will have to plug in a 0 because we have this arctangent. Is that going to do something? Maybe it does, maybe it doesn't. All right, plug in the 2 first. We have 1/2 2 to the fourth minus 3 2 squared plus 3 arctangent of 2. All right, if you say so. Minus, really, this part is, I don't know. I have to really write this down, saving yourself some time. You don't have to either. And then maybe this is going to contribute something. Arctangent of 0, except it doesn't. Why doesn't it? Because the arctangent of 0 is just 0, so it's gone. Why don't I just go ahead and cancel all of that stuff out, because that'll be satisfying. Okay, that's nice. All right, and then let's see, 2 to the 4th, 2 to the 4 is 16, divided by 2 is going to be an 8, minus, let's see, that's minus a 12. This, it's kind of like writing the square root of 3 on your paper. The exact answer for that is just 3 arctangent of 2. So I should get somewhere along the lines of negative 4 plus 3 arctangent of 2. Yeah, so here, you know what? We're going to need some sort of calculator to plug this into, because we're supposed to interpret our answer in terms of area. We don't know if this is a positive or negative number necessarily. All right, so you know what? I'm going to pull out my camera like so. Here we go. And if I remember it, oh yeah, you want to make sure that your calculator is set to radians. Why is that? Because all of calculus is defined based on radians, degrees. If you wanted it in degrees, you'd have to convert it. Okay, so whatever. It was a negative 4 plus 3 arctangent of 2. I think that's what it was. So arctangent right there. Plug in a 2, close those parentheses, and we get an overall negative answer. So it is less than 1, of course. Let's see. So what this means is that there must be less area down below the curve. Okay, right? Not less area, more area below the curve than there was up above the x-axis. That's what I'm trying to say. More of the function is down below the x-axis. Hey, let's go ahead and take a look at that. Shall we? Okay, so if I hit y equals, I have already taken the liberty of typing our function in here under y equals. We could take a look at the graph. Maybe I do a zoom, I don't know, 4. Sounds good. All right, we only care between 0 and 2 right here, so you can see some positive business happening here, some negative, and then some positive. So apparently there's more of this negative right here. Oh, you know what? Since I already have the calculator out, let me go ahead and show you something truly extraordinary. Okay, so again, the name of this function is y1. If you ever wanted it, here, let me quit back to the home screen. If I ever wanted that function, the shortcut is F4. So I hit alpha F4, and there's where they all live. If your calculator doesn't do that, you can get the yvars menu under the vars menu. Just as a recap, that's vars, and then you'd have to go to yvars, you'd go to function, and then there they are too. All right, that's a lot of steps to go through, especially when you can just do that. Okay, anyway, the reason why I bring that up is because here, let me show you something that lives in the math menu. Okay, if I scroll down here, number 8 and number 9, those are our two that we care about in calculus. We haven't actually used in_derv parentheses. Let's see what that does. I'm going to hit the little plus sign. It says, put in an expression, and it gives us a numeric derivative. Whoa, what do you know about that? Let's just say, for example, let's see, it wants an expression, a variable, and a value. Let's just see what it does. I'm going to paste this in. An expression, that's going to be a function. A variable, that is basically what is the variable that I'm going to take the derivative with respect to. And then I want to find where the derivative where, like the slope of the graph at a particular point. So let me just paste that thing in here. Oh, look, it is in Leibniz notation. All right. Let's see, down here at the bottom we need x because it is the variable of integration here. Inside the parentheses you put the function, and remember that we can just call this thing up if we wanted to. Let's see, it's y1, and then here, let's just say that I want to find the derivative at, I don't know, let's find it at 1. Let's find it at 1 here. Hit enter. It's not going to give you a derivative as an equation. Instead, the only thing that it's going to give you is an approximation for the derivative at x is equal to 1. That's it. That's its limitation. Okay. All right. Same thing is true about definite integrals, but you know what? With definite integrals, that's all you need, right? It's never going to find an antiderivative for you. You need a computer algebra system for that. Instead, it can approximate the value of a definite integral, just like it did with that derivative. And the steps here are, I'm going to go to math again, but this time it's number 9. And here, let's take a look and see what the little help menu by hitting the plus sign tells us. It's going to give us numerical integration. Nice. So expression goes inside here. Our variable, it's like the dx part. You just put the variable, whatever it is, a lower bound and an upper bound, and then something called a tolerance that you don't have to worry about. So let's go ahead and paste this in. So that's F4, that's right there for pasting. You could type it in back there on that help screen if you wanted to, and then paste it into the home screen. All right, so you can see that it looks just like it would on your piece of paper. That's real nice. All right, so I'm going to scroll over here. My lower bound was, I want to say it was 0, and then my upper bound over here was a 2. Inside the parentheses is your integrand, which was our y1, alpha F4. Pull up our y1, and then here's where we would put our variable of integration. It is just an x. Now, I will say this before I hit enter. I will say this, and that is, if you don't have the latest operating system here that gives this math print here, yours is going to look a little bit different. It's going to have instead everything that we just typed inside of parentheses separated by commas. Okay. Yeah, let me just go ahead and hit enter. Remember, it should give us approximately this thing that's right up here. Let's see. It sure did. Isn't that nice? Okay, so from here on out, we'll definitely have parts of tests that have calculator parts on it, and these are some of the things that the AP Calculus exam is going to require you to be able to do, is find a numerical derivative and a numerical integral, that's basically a definite integral, using your calculator. Okay.